Hello students, as a part of digital education initiative of Dr. APJ Abdul Kalam Technical University, here is another lecture on subject VLSI technology having subject code KEC 053. In today's lecture, we are going to continue with the assembly and package design as a part of fabrication process of an integrated circuit. The contents of the lecture include what exactly are the package design considerations, what are the technologies which are used for package design, and what are the special considerations associated with it. At the end of this lecture, I expect you to understand and explain the IC package design considerations, discuss the different technologies which are used for package design, and you should be able to narrate the special constraints also, or special considerations also, which are basically considered or which are considered while designing the IC package or assembling the integrated circuit and packaging it. So, first thing, so the key considerations while packaging the or assembling the integrated circuit include, very first is the smaller footprints. Now, we know already as the scaling has happened, or when a device scaling has happened, or integrated circuits have miniaturized, the scaling or the packaging density is also increased, and because of that there is a lot of issue being faced with respect to the bonds or the interconnects which are associated with the device designs. Since these interconnects have also been reduced, the area occupied by because of the integrated circuit is overall getting reduced, and since the operationality or the functionality is increased, the rate of or the operating speed is also enhanced, and that has led to different constraints in the designing. And these constraints are basically being considered while, or these are like to make the overall yield good, or you don't want, like you want maximum outcome from the design of or packaging of the integrated circuit, we have to focus on different issues, and these packages or these design styles include interchangeable pinout designs, or you have something known as the devices which are basically used exploring the threshold voltage, and such designs can directly become or can be directly interconnected to the microcontroller, and that is basically which can save the overall board space. So, this is basically like overall the occupancy of the IC is to be reduced, and in order to achieve that we have different approaches. One of the approach or one of the key constraint in this case is every IC when you are designing, may at any level, may it be interconnect, may it be the layout of the what you call placement of different circuits within the IC, there is a typical VLSI design rules being followed. These are basically layout rules, and there are different packages available. So, with shrinkages in the sizes, increase in the number of input output pins, and space, that is the space required for overall major chip area is basically reduced, and to meet the challenges, that is the pitch, which is basically the separation between the two devices, the effective bonding pad size is also reduced, and there are specific design rules which are being followed for wire bounding. This is encouraged by using different CAD tools, and there are design rule checkers, electrical rule checkers, and layout versus schematic tools which basically ensure that there is proper adherence to the layout being followed while designing the integrated circuit. The typical equation which is being followed, that is the length of focus, that is the dimension of the device, is basically designed by the number of spaces between the pins. So, if you have n pins, there will be n minus 1 spaces, and the interspace between or spacing, the separation between them, that will be deciding the total dimension of the chip, and this is what is being exhibited over here. Another concept what you need to consider while designing is the power density. The demand per power, or you know already the handheld devices have been increased, so they need battery support, and when high operation or multifunctionality is being imbibed or is being included in the IC, then those kind of operations demand a lot of power consumption, and therefore when you have these solar power like battery held devices or handheld devices, battery supporting devices, you need a longer battery life, and therefore you cannot afford to have large power consumption. and therefore you need to have trade off between them, or you need to optimize the power consumption of the circuits which are included or are part of your integrated circuit. And therefore these what you call high power density devices also demands lot of issues to be taken into account while designing the integrated circuit packages. This package also needs thermal efficiency, like thermal behavior of the package intrinsically is tied to its reliability, because component like you have IGBT, that is insulated gate, bipolar transistor, running at low power temperature reduces the stress on the stress or basically stress on the component. The thermal characteristics also impact the heat sink or the size of the low, like if you have low temperature you can have smaller heat sinks. Moreover, lower cooling requirements allow designers to for higher like you can make use of that space, because that space can be utilized for more devices, or you have margin for increasing the power density. So if you don't require any heat sink, then you can have higher power, like you can have or incorporate multiple devices having multiple functionalities. So in how to deal with such kind of issues, or how to address those issues, so that can be addressed by taking into account the modeling of those heat transfer modes, and that heat transfer is divided into different categories. First is the junction to the from package die, that is the to the surface of the package, that is we call it as by heat by like transfer of heat by conduction. And second phase is basically from package to the ambient, and this can be divided, or overall this is calculated by calculating the thermal resistance. Now this thermal resistance is basically calculated by theta JA, that is the theta JA is equal to theta JC plus theta CA. Now what is this theta JC? This is junction, okay, junction to, this is basically junction to, okay, theta JC is basically junction to case, and this theta JC is basically the temperature difference between junction to case divided by power. Similarly, theta CA, that is case to ambient, that is temperature difference divided by power. Now these two components will be together added to calculate the total thermal resistance. So total thermal resistance will be calculated, and you get to know what will be the total power, or what will be the total like requirement, like accordingly you can have the heat sink requirement being defined. So this is again discussed over here. So this is getting addressed, like once you know the heat sink to design, then you can address the heat dissipation issue. So this is, so conventional methods which are used to create isolation in the device packages are often expensive, and you cannot handle such kind of like power when being like a lot of power density issue is being included, or a lot of power consuming circuits are there within the circuit. You need to design the heat sink, and you need to address the issue of heat dissipation. We have seen in the previous slide that it can be addressed by considering the temperature difference, and like theta JC and theta CA, all those things we can take into account. You can calculate the thermal resistance, but only thermal resistance will not happen. So you need to like take into account proper management of the heat dissipation, because from these heat dissipations will be happening from high power density components like IGBT, or any IC package is expected to provide proper provisioning of heat dissipation and isolation, so that the operation of the circuit is reliable. There is no thermal issue involved, or there is no compromise with the thermal what you call like whenever there is increase in temperature, you know the behavior of the circuit will change, and that you don't want to happen. So you need to have provisioning, and that provisioning is taken into account when you consider the heat dissipation. Last is electrical considerations. Now every circuit you need to know, you need to have minimized power losses, or you need to have, like power will be consumed when there is switching activity, especially in case of digital circuits. So these switching losses are you need to take into account in order to boost the package efficiency, especially when you have hard switching circuits which are operating higher than 20 kilohertz, such as industrial devices. Special key aspect in this case you need to know is, you need to take into account low ground resistance. Okay, that means you have to ensure that there is proper grounding being provided, or there is minimum resistance, that is entire circuit like current can be easily grounded. You have minimum signal spiking encountered. You have short signal leads, so that there is no contact resistance or that wire interconnect resistance is minimized. You have short paralleled runs, that means two interconnects if are running parallel, you have minimum, okay, minimum such cases happening, because any switching activity in between these. So this is interconnect 1 and this is interconnect 2. If they are running parallel, then also if the current density is high, that can also have crosstalk, that can lead to crosstalk. So you don't want that to happen, so that also can be minimized. And you not maximum, so self inductance, to reduce the self inductance or reflection to happen, you have to have minimum mutual impedance between these two interconnects which are crossing or which are passing adjacent to each other. Lastly, we need to take into account the mechanical considerations, and these mechanical considerations are basically related to the physical properties of the materials which are used for the packages. Now these packages materials have to have proper thermal coefficients matched, that is basically TCA, that is, we call it as TCE, that is thermal coefficient of expansion. Now this thermal coefficient of expansion relates the stress factor, and any stress associated with elevated temperature is to be properly handled by the package material which is being used. So you have to have a matched thermal expansion coefficient, then you need to analyze the stress related issues, and these stress related issues are generally what you call emulated or simulated using, you have something known as finite elemental analysis or FEA. This is a tool which allows you to simulate them, calculate them, estimate them, so that you can address all the process related design design related stresses, and you can prohibit or you can what you call countermeasures can be taken into consideration while designing against these stress related failure mechanisms. Then once these 6 constraints are cleared, that is VLSI design rules for smaller footprints, electrical, mechanical properties, heat sink, thermal what you call thermal behavior, heat dissipation, all those aspects have been designed. We need to package the particular integrated circuit. So very first thing is wafer preparation. So wafer preparation means once your wafer is ready with the circuit, whatever with all unit processes over, first what we do is we before packaging the wafers are thinned. Typically we like 12 inches wafers are being used in fabrication, and they are normally 650 to 700 micrometer thick initially. But the thickness while handling the wafer fabrication is large, but after that only within some few micrometers or like 100 micrometer area only you will have your entire circuit getting fabricated. Rest of the wafer is not to be used, or that is to be thinned, and therefore front side is first protected using some thick resist or some other protective material, and then to prevent the cracks, and then the wafer thinning is being carried out. So first thing is wafer thinning. So this is how your wafer thinning is being done, and then your wafer is having those scribed lines. These are the scribed lines. Against these scribed lines, the wafer will be then like those chips. So each of these, okay, this is entire one integrated circuit. This is one integrated circuit. So you need to first, okay. So scribe lines are basically separating, and these are then we call them as die. Now these are dies which are separated thereafter. And this is how you will based on these scribe lines you will be what you call cutting them, separating those ICs. So this is basically the die separation. So this die separation is after thinning you carry out the individual dies you separate, and each individual die is then chosen or tested for exact functionality. All those which are misfit or which are failing the test are again re-evaluated, so that entire fabrication process where what has gone wrong is to be properly tested or properly what you call investigated, and that investigation is a major thing which is essential for improvising the yield, and that is mandatorily to be done. So this is what is the isolation. So every integrated circuit, whatever defects are, okay, so you are sorting the die and identifying all the good dies or good integrated circuits which are there. Then you separate them, all the integrated circuits which are good ones are separated and bad dies are usually scrapped and the silicon is reused. This is okay, this is how you carry out the, then you inspect those dies for cracks, defects, and good dies are basically used for further packaging. So prior to packaging, these dies are then attached. Now what is this attachment? They are basically mounted on something medium which is either ceramic or some medium which can establish electrical contacts subsequently. So you have something known as ceramic substrate, and so that you have strong bond between the die and the package. So you cannot have simple integrated circuit loosely like just like that fitted into the package. So first it is attached to a mounting what you call mounting medium. Now this mounting medium is generally ceramic or some other like specific material. That material can be conducting or non-conducting. You have, so this is basically a precursor for the wire bonding process, during which electrical leads are then attached. For flip chip process, okay, the die attached and the bonding process is combined. Bonding is basically you are establishing the contact. So this is what is the, so you are, okay, this is what is the bonding process. These are the bonding wires. So every chip will have bonding pads, and this is how subsequently you will have these interconnect pins. These are the pins, external pins, which are connected to the, so like which are making this integrated circuit accessible from the outside system. So this is what is the schematic. Then the die attachment, they are hard, they can be hard soldered, or you can have non-conducting such as epoxy adhesives can be used to attach the die to the package. Then once you attach, you have bonding. The bonding wires are then connected to the leads of the IC, so that IC can be electrical connected to the outside devices or other circuits. Bonding usually follows die attach, or two steps are combined in a flip chip process. Both attachment as well as bonding will be combined together in a flip chip process. There are different techniques used for bonding, that is the interconnection of wires, and that is known as wire bonding, tape bonding, or flip chip bonding. So these are the three techniques of bonding. So first we have separated, then attached on a mounting substrate, and once you have mounted it on a medium, you have then bonded it to the wire. So this wire bonding is being shown over here. This is the chip, see, this is the die, and you have a ball mounted on it, and through that you are mounting, okay, this is the inner lead and you are having this kind of connection. This is the gold wire bonding to a lead, and this is called as ball bonding. The gold wire is fed through the capillary. This is the capillary through which the gold wire and forms the bond with the metal lead on the package. Okay, this is how your bonding will be created. Another one I told you about tape package. Now tape package is basically, this is the lead, these are the leads, you have this thermode, and this is how, see, this is this reflowed solder bump, there will be solder bump, and then you will have these kind of pads. So this is the tape band, this is a thin device fabrication where leads are deposited on a flexible tape. These leads are deposited on the flexible tape and they are stamped onto the pads. Then these are the, see, these are the pads, and then you are creating a solder bump, and then you will connect it to the external environment. So this is how you will have double process. So these are the different techniques. Now different packaging design styles or fabrication technologies are being used. First is the ceramic package technology. It is very common, very effective, cost effective for constructing all kinds of complex packages, and it is okay, it is very good, like mostly being used for all the packaging. You have a typical what you call molded molds available, and those are standard packaging styles are also available, and ceramic packages are predominantly used in majority of the ICs. Second thing is your glass sealed package. Now glass sealed package is something where you are having glass sealing being used for basically two ceramic units are being pressed, and there is glass sealing between them, so that the package is properly airtight or hermetically sealed, and that is what is basically gas sealed. Now glass sealed is further reducing the cost and reliability of the device. because it is completely sealing the entire or making that particular integrated circuit airtight. Then you have something known as plastic mold technology. Plastic mold technology is also similar. You have molded plastics, like it is further like reducing the cost and helping you to design the complex circuits. So this is one of the technique. Another one is the molding process, through which your typical molds are available, through which you are integrating or packaging those devices. And lastly, you have something known as plastic composite technology, which are being used for specific devices, or which is preferred, basically they are heat resistance, or you are like you have better electrical insulation being provided. It has got good heat what you call handling or heat dissipation, or handling heat dissipation in a better manner. Therefore, these plastic composite packages are the latest ones which are being used. So this is basically, as you progress, you have got new advancements happening in the packaging technologies, and that is how you have different kinds of packages being designed. So ceramic package will have all these ceramic what you call properties being incorporated. You have insulating. Ceramic behaves as a good insulator, so your packaging will be properly what you call have good what you call insulation. But then that improvisation is being done by providing glass sealing. Then further improvisation is, or cost effectivity is being introduced using plastic mold technology. Enhanced molding processes have been used in molding processes, and finally you have got something known as plastic composite technology, where you have better heat dissipation being encountered, or better electrical properties have been incorporated. So lastly, when all the entire fabrication is being done, you have some special considerations being taken into account. Now these special considerations include cleaning, ceramic package lid sealing, encapsulation, alpha particle protection, assembly environment, and miscellaneous operations. Now what are these? One by one we will see in brief, and then before we wind up, let us check out what exactly these things are. So cleaning is essential everywhere. You have seen already in the first unit itself, where we have considered separate cleaning, because it is the essential component of IC fabrication. Here also, before packaging, you must have cleaning, and cleaning addresses two major issues. One is it eliminates the contaminating impurities like organic impurities which may corrode the metal contacts in turn, and secondly, to prevent the or to preserve the electrical properties, you need to remove the ionic impurities also. So for both cases you need cleaning to be done, and this is an essential part of before packaging the IC. Secondly, you have something known as package lid sealing. Now when you are designing a ceramic package, it has to be airtight, it has to be hermetically sealed to prevent any corrosion, to prevent any metal coming in contact with oxygen, so that you need to prevent any what you call unreliable operation from the IC, and that is why this sealing is essential. Thirdly, when sealing is not being done, you have something known as encapsulation or enclosing it into silicon. Now normally silicon is used, or is used for encapsulating or covering this particular integrated circuit, so that it is properly what you call covered or isolated from the external environment, and there is minimum impact of this what you call package. The package may contain some what you call contaminants which may hamper the properties of the interconnects, and you don't want that to happen, and for that reason you need to seal it, and that is essential in some applications where you have what you call your high what you call precision applications, such as space application. If your electronic circuit is being used for high altitude or some critical applications, you need to take care of it, and that is why you need this encapsulation process to be carried out. Thirdly, you have something known as alpha particle protection. This alpha particle protection is basically because of the alpha particle radiation happening because of the packages, like whatever packages you are using, ceramic packages, if they have some what you call radioactive such as uranium or thorium particles what you call radiated, in turn can happen compromise the reliability of the device, and to prevent that you need to ensure that such kind of particles are not going to affect overall operation of the device, and the package is free from these particles. To prevent them, you need to carry out proper processes, cleaning processes for preventing such alpha particle protection. Then then comes the assembly. So, any particle size in the environment approximately around 1 micrometer can damage the assembly process, and therefore, you need to eliminate. You have already studied the clean room process, which is an essential requirement. So, any particle size that can affect or that can in turn compromise the reliability of the device operation, we must prevent that to come in contact with the package. While during packaging, you must prevent all that thing. So, and therefore, you have to have you have to ensure that the environment is clean, it does not have any particles of size 1 micrometer or higher than that, which can in turn affect the operation, like compromise the reliability. And lastly, miscellaneous operations. These miscellaneous operations include leakage test, electrical test, then you need component marking systems, you need lead scanning, okay, or basically for quality check, then handling the IC packages through the electrical testing, and moisture measurements which are to be carried out. So, one of the like when you carry out encapsulation, you ensure that there is no moisture also. In fact, in ceramic lead packaging also, you have to ensure that the packaging is like the sealing is to prevent any moisture content getting in contact with the interconnects or leads or wire bonding process, which is connecting the IC to the outside world. So, these are the miscellaneous cleaning processes. So, before we end, let us check out if you can discuss the key points taken into consideration while designing the IC package, if you can narrate the processes which are involved in assembly and packaging, and you can consider or you can elaborate or you can narrate, describe the special considerations which are required while designing the IC packaging. We can proceed further with the device, like further finalization of the device and CMOS, what you call fabrication of CMOS in the next lecture. So, God bless and good luck.